So, ladies and gentlemen, let us go to the second talk of this session. We will move forward from front end to the back end. And we have a distinguished speaker, Dr. P.K. Wattal. He will be speaking us on reprocessing of irradiated Thoria bundles from power reactors in India. Dr. Wattal was the former director of Nuclear Recycle Group of Bhabha Atomic Research Center and expert in the field of processes and technologies for back and fuel cycle addressing reprocessing and waste management, particularly on the radioactive waste. Dr. Wattal, please.
Thank you, Chairman. It's my pleasure to address this gathering on our experiences with respect to the thorium reprocessing from the PHWR reactors. Let me first tell you this is the first of its lecture, even in BARC, that I am delivering. And I have a conviction that this is the first experience of the world that what we have seen. I'm also delighted to see Dr. Banerjee, Sri Mehta, and many other seniors who have been my mentors. I will not put much of time because Dr. Banerjee already stolen this aspect. But the point is these numbers are very important. And definitely even if the thorium-based sip and fuel is directly disposed of because of the better stability, it can be accepted in the geological repository. Now, this also has been deliberated that we have done number of thorium bundles put in the PHWRs for the flux flattening, and these are the bundles which are ready for us for the reprocessing. Now, what these bundles have seen? These bundles have seen irradiation 8,000 megawatt days per ton to 11,000. The last bundle we processed had seen an irradiation up to 11,000 megawatt days per ton. They are like our bundles in the PHWR uranium bundles with 19 pins, bundle diameter almost 80 millimeter, and weighing 15.3 kgs. And the thorium-233 content is almost 13.5 kgs, and uranium-233 associated with it is 80 to 140 grams, depending upon where they are located. The beta activity, 3,000 curies per bundle, gamma activity, almost 700 curie per bundle. In the last thorium conference in CERN, I had said that we have already reprocessed the irradiated thoria that has come out of our research reactors. And that was done in a dedicated facility called uranium thorium separation facility. And we could recover almost entire uranium-233, but the only difference was that the U-232 associated was 2 to 3 ppm. So in a way, it validated our flow sheets, it validated our separations, but it did not involve the shielding because of 2 to 3 ppm. And subsequently, we had already started building a dedicated facility for the reprocessing of the thoria bundles in the power reactors, that's PHWRs, and where uranium-233 obtained is 165 to 265 ppm, because the subsequent batches we are getting uranium-232 of the order of 260, 255 ppm. And it is not only a question of separation of uranium-233. From the raffinates, we have also recovered quantitatively the thorium. Thorium has not gone to the waste. What has gone to the waste are the fission products. I will come to that later, because even though we have abundant reserves of thorium, we value thorium. We cannot subject it to the waste streams, and also when we do the vitrification of these wastes from the thoria reprocessing, we don't want the glass to be loaded with the thorium. What you see here is the facility where we have processed the fuel irradiated in the research reactors. And what you see here is a typical cell view, because the plant is too big, where we have carried out the reprocessing of the thoria from the power reactors. Of course, this is a shielded facility. I will come more on that. I have truncated the detailed layout of the plant, but what is more important I wanted to show is that we have in this plant 3 cells. One, this is a transfer cell, and this is another cell. 1, 2, 3. And the bundle, irradiated bundle, will come in the shielded cask, which is called the transfer cask. It will get latched to this point. I'll show you the photograph. And then it will go to the transit cell or intermediate cell, and from that, the bundle will go to the cell 1 for chopping, dissolution, and then it will go as a solution to the cell 2, where it will be separated. Then there is a third facility, which I have highlighted here. This is the reconversion facility, where uranyl nitrate solution obtained in the solvent extraction is converted into the final product of uranium oxide. Now, to this gathering and to the people who know the reprocessing, because yesterday there was some debate, I wanted to share that thorium reprocessing and uranium reprocessing, there is nothing great difference. Because all along in these deliberations, I have been listening that thorium has a challenge of reprocessing. Now, where is the challenge? Let me say, and then it was also deliberated that a lot of shielding is needed for the thorium reprocessing. It is perhaps not exactly the same, because any reprocessing what you do, and you talk about the uranium, these up to the solvent extraction anyway is done in the shielded cells, in the concrete shielded cells of 1 meter, more than 1 meter length. What is difference is this reconversion, where for the plutonium, you reconvert into plutonium oxide, it is done in the glow boxes, which are not shielded, which are only alpha tight. And for the thorium, this reconversion lab has to be shielded, because when you handle uranium-233, you are expected to handle uranium-232 as well, which gives gamma dose. So to sum up, this plant has 2 portions, the main building and the extension. It has its own dedicated stack and its own waste tank form of huge 5 tanks of 5 meter cube each. Why there are 5 tanks? Because we segregate the waste. We right from the beginning, put it in the separate tanks. And in the main building, there are process cells, 1 and 2, as I said, chopping of the fuel, charging, exhaust, off-gas, and all that. And in the extension building, we have what's called the reconversion, shielded reconversion laboratory, which are nothing but the shielded glow boxes where we finally convert the uranyl nitrate to uranium oxide. Now, well, this is the reconversion shielded facility. Of course, first of its kind in India. I don't know abroad, but first of its facility in the world where we have handled uranium-233 with uranium-232 up to 260 ppm. What is the difference? These are all inside are the same glow boxes, what is needed for the uranium reprocessing, excepting that it has 75 mm thick MS shielding. And all the operations are carried by the master slave manipulators. And this is inside of a cell. Of course, when we process inside a concrete cell, it has to be all remote. This is the typical. Now, before I go, how we reprocess and what are our experiences, I got very much interested in a review, a paper by ORNL, a review of thorium fuel reprocessing experience. Unfortunately, I could not get the year. But what he says is, thorium reprocessing is nothing new. See, by 1950, if you see 1950, a pilot plant was operated to separate uranium-233 in kilogram quantities from irradiated aluminum-clad thorium metal slags. This aluminum-clad is very important. By 1964, uranium-233 demand to fuel experimental reactors exceeded the supply, and aluminum-clad thorium oxide power was processed at Hanford and Savannah River to recover 1.4 tons of uranium-233. And Dr. Balraj Saigal tells me, which I could not find, that in US they have also reprocessed these Thoria bundles with the zircaloy clad, but it is not there. By 1969, 17 tons of SS clad thorium oxide pellet fuel from Consolidated Edison reactor at Indian Point, New York, was reprocessed at privately owned nuclear fuel services plant at West Valley, New York. So then the same report says these flow sheets are satisfactory for processing aluminum clad thorium, but are not suitable for power reactor fuels that require stainless steel or zirconium alloy as cladding for the fuel. Now, why this statement they have made? On one hand, there is a statement that these flow sheets are satisfactory for processing aluminum clad. What is the difference? I will come to that. It further says, and that is very, very important, several large campaigns have been completed to recover uranium from the irradiated thorium. All were conducted in existing Purex equipment. That is the crux of the matter, which is designed for optimum effectiveness in uranium reprocessing, but is not suitable for the thorium reprocessing, as Dr. Banerjee said in the morning. Because if you really don't do it and you find PHWs or BWs are more effective, you give thorium the last priority and it will not come up. And this is exactly what they did. They did it as a campaign, did it in the existing reprocessing facilities which were not equipped from the shielding point of view in the reconversion labs, and started saying that it needs a lot of shielding, it needs a lot of concern. But the fact remains. One more point, which definitely is not true now. One important area, a nitrate solution of zircaloy clad thorium oxide fuel for solvent extraction. He says the dissolution of thoria is accomplished with fluoride catalyzed HNO3. This dissolver solution will also attack the zircaloy cladding. That's all right. Since zircaloy in solution forms a strong complex with fluoride, it is possible that thoria cannot be completely leached from the cladding in this system. They have not done it, they have postulated it. But I will come back that this statement need not be correct. Then he says at the end, demonstration of several viable flow sheets provide a sound technological base. That's true for the development of the optimum reprocessing methods and facilities. So what I wanted to tell you is that all these things have been done, but they have been done in makeshift arrangements, in retrofitted environment, and that is why there is a lot of apprehensions, and even those apprehensions are quoted today. Now let me go with the journey of how we did it. We got the safety clearance somewhere in middle of December 2014, and it was on 12th and 14th January that we have first of all transported all the bundles from the reactors in our fuel pool at Trombay, and then this transfer is within the Trombay from the fuel pool to our reprocessing plant. And we had the casks, which we carry 2 bundles at a time, and contact dose was 5 to 20 mR per hour because this is within our BRC premises. And of course, when we did the chopping, I will deliberate more on that, there was no activity discharge from the stack. This is the cask which carries 2 bundles of irradiated thorium. Mind you, we have around 260 bundles available, and this is transport within BRC premises, taking it to our reprocessing plant, dedicated reprocessing plant for power reactor thoria reprocessing facility. This is how impatiently we are waiting for the flask to get latched inside. This is a area which is well ventilated. The truck will go inside. the cask will get latched, I will show you, and finally it will go inside the cell. This is the fuel cask, which is latched to the external of the cell, and the fuel will be transferred mechanically inside the cell for further processing. Now, this is also very interesting, and we have done it first time. We did the laser cutting. You see, the fuel bundle has an end plate, which has to be first cut. And that should be very precisely, because those who know the processing, if the fuel bundles get crimps at the end, then they still retain the material on those crimps, and that gives dose to the hull, we call it. So we did first the online grid cutting by laser methods, precise. Then we did the laser cutting operation. I will show you that, of the zircaloy bundle in the hot cell. This bundle end plate after cutting operation. This is the end connections, and finally dismantling of the bundle into pins inside the trolley. You see the trolley, the pins fall, and you see the pins over here, which will finally go to the chopping. This is how the laser beam cuts the fuel bundle. This is that 19 pin fuel bundle. Now come to the dissolution. Another area which people have been talking, dissolution of Thoria is very difficult, and that is why the concern. But to us, I don't think our experience is like that. Let me show that we got these Thoria bundles after chopping dissolved, and we could dissolve 99.5%. So there were no issues like if the zircaloy forms a complex with the Thoria, and then that will find very difficult in the solvent extraction. We did not face that. We had a dissolver capacity of around 500 liters. We did 4 bundles as a batch. We did 2 batches because that was our safety requirement, that you demonstrate 2 batches and then come back to us for the further. Dissolution per batch was around 60 hours, and we did not get anything like pressurization or anything. The negative pressure was very well maintained inside the dissolver. Now, the point is that when you do the dissolve, another aspect they have said that it has to be fluoride-induced dissolution because Thoria doesn't dissolve. As a matter of fact, that's true, but the question is, all along, ORNL or US has talked about fluoride concentration of 0.03 molar. Is it correct or it is not correct? In that Global 2014, I had a chance to, I forgot the name, talk to the gentleman from ORNL, who was very old fellow who would not even hear properly, and who had done these experiments first time, and he had arrived at 0.03 molar concentration. I asked him, sir, what was the basis? It is 10 times, 15 times the stoichiometric requirement. He told me he was not sure about the dissolver material. So he wanted to be very safe and added sodium fluoride for better dissolution, and added sodium fluoride for the aluminum for the complexation. Anyway, what is the concern of fluoride and aluminum? Fluoride, not much from the corrosion point of view here, because you add aluminum nitrate, it forms aluminum fluoride, and it doesn't sort of volatile at that point. But in the waste streams, this aluminum and fluoride could be problematic when you subject it to the vitrification. I will come back on that. But what is important is that even with a fluoride of 0.005 and no aluminum, you can still get the dissolution. Only thing is it takes a little more time. Or for that matter, if you see that aluminum nil, the curve C, fluoride, even if you maintain 0.03 molar but don't add any aluminum, it is also all right for the zircaloy clad fuel, because zircaloy complexes with the fluoride and does the same work as aluminum. Now coming to the solvent extraction, we used 5% TBP, we scrubbed, stripping is nothing great. Those who do the reprocessing day in, day out, only thing is, as against 30% TBP, we use 5% TBP, that is from the chemistry point of view, and the product recovery was 94%, and overall DF was 10 raised power 5. Of course, I have purposely given these numbers. What is that A/O ratio, those who are familiar with the solvent extraction. Now this is the whole gamut of operations which you have to do in the shielded environment. That's called the reconversion. So you have to do feed conditioning, conversion, precipitation, filtration, and calcination. And operations can be very comfortably done because the moment you have done the solvent extraction and within 2 days, if you do these operations, the dose doesn't build up that much. So these are very normal operations. You do it, and this is how we have done in this reconversion shielded lab, which has the manipulators, and we could finally achieve the final product. This is the final product of uranium-233. This is the first batch. The second batch has something like 260 ppm of uranium-232. And remember, this facility, that reconversion facility, is designed for 500 ppm of uranium-232. Now we have also, of course, this is a patent, we have also done typical charcoal-based thoron mitigation. This is the radiological impact. We need not release anything through the stack. We can definitely absorb everything on these charcoal filter beds. You can see this is the input radon activity, and this is output. We got a factor of initially 10⁻⁴, which finally stabilized at 10⁻⁴, and practically nothing was released during our solvent extraction. This mitigation we had put in our solvent extraction system, but it can be put to the chopping, it can be put to the dissolver, it can be put anywhere, and this was the reduction. See, the thoron release through the stack was 10⁻12 becquerel as against 10⁻14, and the dose on the cell walls was less than 1 mR, and in the off-gas pan was 3 to 4 mR per hour. And this is how the dose builds up with time because of the uranium-232 concentration. I have taken 0.2 kilograms, that was a batch with 165 ppm. We made a calculations and actually validated it over 3 months time, how it is building up. So what is important is around almost 4 or 5 days, it doesn't build more than 100 mR per hour. Now, quick look on the vitrification. As I was telling you, aluminum nitrate, thorium oxide, and fluoride. These are the little concerns for a person who knows the vitrification. If these concentrations are very high, it may impair the solubility limits in the glass. But we developed, and also when we do the vitrification, the fluoride doesn't have the problem of solubility, but fluoride has the problem of volatility because vitrification is carried out at very high temperatures. We found that in the laboratory, it was 7% overall volatilization, but when we did actually, it was less than 3%. And this is how we separated the thorium, and we also converted into the glass. We converted 18.3 cubic meters of thorium lean waste because we removed the thorium. We made it in the borosilicate glass. In fact, the chairman, Dr. Sinha, showed this slide. Solubility limit of thorium in the borosilicate glass increases with the addition of barium. So if you use barium borosilicate glass, there is no issue about the thorium or aluminum, even if you don't remove the thorium from the raffinate stream. So the current status is that 4 irradiated thorium, actually 8, not 4, the uranium solution processed and converted to the oxide, uranium oxide powder containing U-232 stored, safety clearance for routine operations is anytime we expect it. So the conclusion is that we have to have the closed fuel cycle and the thorium utilization. And I can tell you that the proliferation resistance associated with the thorium and also the sort of the abundance availability will definitely outweigh if we debate that the fuel fabrication cost slightly is up because it has to be done in the remote fashion. But for the India, there is no choice. So we had to maximize use of existing resources, and of course, there is not much of radiotoxicity reduction. There's definitely plant, design, everything was done over a number of years, and many people got involved. This is the nuclear recycle group, nuclear recycle board, and definitely I would acknowledge the radiological physics and advisory division who did make that charcoal-based thorium radon mitigation. Thank you for your kind attention.
Thank you, Dr. Wattal, for your lucid talk on the reprocessing of irradiated thoria bundles from the power reactors in India. Now the floor is open for any clarifications. Yes, please.
I just want your statement on the typical reprocessing recovery efficiency for U-233 in the irradiated thorium, because we talk about 1.03 and so on in thermal breeders, and if there is 3% loss, then it's gone. So what is your realistic assessment of the recovery efficiency of U-233?
I think I made that presentation. 99.5% more than that we have recovered. It is as good as what you recover plutonium from the uranium reprocessing.
So as an expert, you think this is industrial, at an industrial scale, this number is applicable?
This is an industrial scale operation.
Okay, okay.
Anytime you will do the reprocessing of irradiated thoria from PHWR reactors, this is what you have to do.
Okay.
These are the actual bundles from the PHWR reactors, seeing that burn up of 11,000. I said that in the first slide.
Thank you.
Any other clarifications? Yes, please.
Sir, it was a very informative presentation. You are told that you have constructed a facility to handle up to 500 ppm of U-232. What about the advanced fuel cycles which may come higher ppm of U-232? What will be the future course of action?
It is very simple. It is very simple. I will tell you what. First of all, 500 ppm of uranium-232 contamination, you have to see what type of burn-ups it gives. Right? Now, up to 11,000 megawatt days per ton, we have got so far only maximum 260 ppm. Of course, we have to reprocess many more bundles, but 11,000, we did one with 8,000, one batch with the 11,000. These were the extremes to see the concentration. Right, now with 500 ppm, as I said, the reconversion lab shielding is 75 mm. Right? Now we can definitely go up to 100, 120 mm with our remote handling gadgets. So if uranium-233 concentration is little more, the shielding we will increase. That is what it is.
So you have to construct a separate facility, or you can augment the existing facilities?
See, the fact remains that our thorium utilization program in the reactors is an ongoing process, right? Currently in the PHWRs. Now, we have not put it in LWRs and all that so far. We don't have. Now, so far the bundles keep on coming. We can reprocess them in this facility, right? Now, if there are more load, we can definitely make one more facility here, rather than augmenting this facility. Not necessarily. It all depends upon, or you can augment the reconversion because the cells are same, whatever it is. You can augment the reconversion facility with a better shielding. That is what it is.
Thank you, sir.
Yes.
Dr. Wattal,
Yes.
what was the batch size in the reconversion step? You had 4 to 8 bundles that were chopped and then were moved towards the reconversion plant. What was the batch size?
400 grams.
400 grams.
400 grams of the final oxide powder.
And they were remaining how long in the reconversion step?
In the reconversion step, it was for 2 days.
2 days, 400
Yes.
grams. So you're multiplying the reconversion cells if you have to have a higher throughput amount.
No, the point I wanted to make is that when you have to handle uranium-232, you cannot idle away time because the dose will keep on building. Now, you have to see, we had made a very calculated guess that up to 6 days we can do, this facility can take the reconversion, converting into the oxide without any external dose to the people. So, and basically we know that it is a job of 2 days. But still, because we are doing it first time, to the safety people, we had showed that up to 6 days, that is 100 MR dose when it comes, it will be still handled by this thing without giving any exposure to the personnel, because the shielding of 75 mm thick was adequate up to 500 ppm, which is equivalent to, if you have a 250 ppm level, it is equivalent to 5 days or 6 days, even if the thing has to remain there. So that, and it doesn't take more than 2 days to finish the batch. And once you have removed the batch, then there is no dose, you push the new batch. And this 400 grams came out of 4 bundles in a batch. 4 bundles means thorium-wise 60 kgs of reprocessing. And if you see the numbers, Dr. Banerjee said for a reactor, we need the whole reprocessing plant for is around 20 tons of per year generation if we go to that sort of scenario.
Thank you. Yes, please.
Very
Excuse
good
me.
talk, sir.
Can you give that mic to him first? Then I will come to you.
Yeah. Okay, I can. Very good talk, sir. One issue of this thorium-U-233 fission process, one thing that is talked is it will give to less number of minor actinides, this plutonium and other higher actinides. What is your experience of that?
Yes. These are the figures. I precisely want, sorry. Oh, sorry. These are the figures. If you see, Dr. Banerjee also said, there is nothing like experience. These are all facts that if you have a 60 gigawatt per ton BAR, and if you have uranium cycle, and if you have a thorium cycle, the minor actinides are neptunium, americium, and curium, which is very important. If you see, the yield here is 900 grams per ton as against 3 grams. It's a big difference. Americium is 470 grams from the uranium cycle, it is 0.002, practically nil. And if you see the curium, from 220, it is 0.0006. So this is the minor actinides.
This is what is found after reprocessing.
Our minor actinides are much less because we have not gone to the 60 gigawatt.
Yeah.
Yeah.
That is
The last question, please.
Yeah. So this Thoria bundles contained some percentage of PU, right?
Thoria bundles don't contain, these bundles don't contain any PU.
Okay.
No,
It was
they don't contain. Of course, let me also tell you that we have done 3-component reprocessing also. But the bundles I am talking about, they don't contain plutonium.
Okay. And any idea about where does plutonium go in this scheme?
We did the complete analysis of the product. In fact, it was done by radiochemistry only. It doesn't contain it.
Okay,
We have
thank
not, plutonium has not been reported.
The first PE, it was done on Kakrapar thorium bundle long back in 2003 or so. At that time, I think the burn up was about 8,000 megawatt per ton, which is similar to yours. We used to hear the boron, U-32 content as 490 ppm or close to 500. It has reduced. Is it natural decay or can it decay so fast?
See, the 2 points I wanted to, in fact, I have told. What we have done that time, and that is how we designed the plant for 500 ppm, we shifted the premises from one place to another because of the shielding advocacy, and that was based on a small pin which was reprocessed in a glow box way back and reported 500 ppm. But today, we have seen that we have processed 8 bundles, not a small pin. 8 bundles means 19 into 8, so many pins, and that to full pins, and we did not get. In fact, I was talking to my colleagues that it is better, now we have the actual experience, it is better to see what cross sections you had taken, what spectrum you had taken in your code, and validate that code, because these are the actual numbers that we have observed. So the analysis of one small pin many years back doesn't necessarily mean that that is a, of course it's an indication, no doubt about it.
So that number stands revised.
Pardon?
That old number stands revised. Now this
No, why that old number stands revised is basically, now these are the actual numbers done on an industrial scale. So all I'm saying is when you arrived at an estimation of 500 or based on the values, first of all you validate the code. You see whether it is matching. And if now these numbers are there, you see where the correction factors have to be applied.
Okay, thank you, Dr. Wattal. Seeing is believing, and after seeing all the work has been done, I think a lot of curiosities have been developed. We once again thank Dr. Wattal for his very wonderful presentation. And on behalf of the organizers, it's my pleasant duty to present a moment to Dr. Wattal.